when we have the chain rule for derivatives, we usually have a function f that was composed by a function g of x, and then by chain rule we had that it was the derivative of the composition, it was going to be f prime composing g times g prime of x. Now we're going to have somewhat the opposite. We're going to have that we have a continuous function f, and we're going to have we're going to see that we have some sort of composition inside with a function g of x, and this nearby we're going to have the derivative of g prime. So if we make u equals to g of x, then we can make the transition from the integral being in terms of the variable x to the variable u. Here g of x becomes u, and g prime of x is going to be du dx. So we can transition g prime of x dx for just du, and then we're gonna do the integral in this new variable. So you might be wondering what's the benefit of that? Well, the main benefit of that is that we can transition a very complicated integral in one of the antiderivatives that we know. So how's the procedure for the substitution rule? First, we have an indefinite integral involving a composite function f of g of x. We identify who's going to be the inner function u of g of x, such that a constant multiple of g prime of x is going to appear on the integrand. We substitute u equals g of x and the u equals g prime of x dx in the integral, and we're going to evaluate the new indefinite integral with respect to u. Then at the end, when everything is said and done, we write again everything in terms of x by replacing u by g of x. Okay. Now, disclaimer here, not all the integrals are going to work with the substitution rule. This is just a technique to integrate. So now let's see some examples of integration here with this rule. First, we're going to have the integral of twice 2x plus 1 cubed dx. Notice that we can see that this is not your typical antiderivative because we have a power, but we have a power with something inside, so it's not that easy to manage. So what we do is we can identify that it has something inside, so we're going to make that inside function, that inner function u. So u is going to be 2x plus 1, and so if we take the derivative, the u dx is just going to be 2. And so the u can be seen as 2dx. So now notice I have the 2 here and I have the dx here, so I can rearrange this to be 2x plus 1 cubed times 2dx. And now I can replace this by u cubed times du. Then at this point, notice that transformed into one of the antiderivative that we know how to manage. This is going to be u to the 4 over 4 plus c. And once that we're done at this point, we can go back to the original variable. And so this is going to be 2x plus 1 to the 4 divided 4 plus c. So now let's take a look to another example. Let's go for 10 e to the 10x. So we know a lot of how the exponential function works. And we know that the derivative of e to the x is e to the x, and that the antiderivative of e to the x is e to the x. But if we have a composition with something else, then it becomes somewhat different. So if we do u equals 10x, then maybe we can get rid of this and just have e to the u. That will be the goal. If we do that, then the u dx is just going to be 10, and therefore the u becomes 10 dx. Now with this, I can replace this and this by du, and just transition to have e to the u times du. Remember, 10 and delta x are transforming into the u, and this 10x becomes u. Now, here I can go ahead and do the antiderivative that we know. The antiderivative of e to the u is just e to the u plus c. And then next thing is recovering the original variable, replacing u by 10x, and we're done. Now let's go for another example more. We're going to have x to the 4 times x to the 5 plus 6. Let me just move this ahead. So integral of x to the 4, x to the 5 plus 6 to the 9. So as you can see, this is a power. And it's a power of something polynomial. So the easiest thing is to take that as the inside function, the inner function. And notice that when we take the derivative of that, we're going to get something that is in terms of whatever we have outside. We have 5x to the 4. Notice that we only have x to the 4 over here. So what we can do instead is, when I write the u, is x to the 4 dx. And so what I do is I move this 1 over 5 over here. And so now I'm going to have 1 over 5 u is x to the 4 dx. So that transforms this into u to the 9 times 1 over 5 du. And so that simplifies a lot of the things. And now I have 1 over 5 u to the 9 du, which is a power that we can very easily transition with normal antiderivatives. And this is going to become 1 over 5 u to the 10 over 10 plus c. And now I'll go back to the original variable. So this is x to the 5 plus 9 power 10 divided by 50 plus c. Another example. Let's use the integral of cosine cubed times sine of x. So notice that we can now include certain products as long as they're going to be playing nice with the antiderivative notation. And they're related with the other function by being derivatives or antiderivatives. So if I have cosine cubed here, obviously the candidate for u is cosine because it's the one that is being power to the 3. And if I do that, the u dx is going to be minus sine, and that reflects that this is good because sine is showing up in here. So now the u is minus sine of x dx. And I don't have the minus over here, so I can just transition that to the other side. And minus du is sine of x dx. Now, with that plane, I can transform this into minus, from this minus over here, u cubed, and sine of x dx becomes the du. Then I can use the power rule over here, and this becomes minus u to the 4 over 4 plus c. And then the last step again is transition to the original variable. All right, so this is the main idea of the substitution. In part 2, we'll see some more examples of how to deal with more advanced substitutions.